Welcome back. Today we're looking at enums, short for enumerations, and the pattern matching that makes them so powerful together. These two features, taken together, are the thing that most often makes people fall in love with Rust. If you've only used enums in older languages like Java or C, where an enum is basically a list of named integers, prepare to have your expectations expanded. Rust's enums are much richer. Where structs let you say a value has all of these fields. A user has a name and an email and an active flag. Enums let you say a value is one of these variants. That's a huge idea. It lets you model state that naturally has options. A shape might be a circle or a rectangle or a triangle. A message might be a quit, a move, or a write. A result of an operation might be a success or a failure. Combined with Rust's match keyword, enums give you total compiler-checked confidence that every possible case is handled. Enums are also the foundation of two of the most important types in Rust's standard library, option and result, and we'll meet both in this lesson. You define an enum with the enum keyword, followed by a name in upper camel case and a list of variants. Each variant can be bare, like an ordinary tag with no attached data, as in the direction enum you see on screen with north, south, east, and west. Or a variant can carry data, a tuple of values, or named fields like a mini-struct, or even an entire struct's worth of associated values. This makes enums far more expressive than the labeled integers of older languages. Type theorists call these sum types. A value is one of these variants exclusively, and the compiler tracks which one it is. The message enum on screen shows the full range. Quit is a bare variant, just a tag. Move carries named fields X and Y, like a mini-struct. Write carries a single string, positional. And change color carries 3 U8 values as a tuple. Every variant of an enum is stored in the same way. Rust uses a tag to record which variant is active and allocates enough memory for the largest variant. You access variants through the enum name with a double colon, message : move, and so on. This consistent syntax means you can always tell when you're looking at an enum variant versus a regular function call. Rust doesn't have null. Let that sink in for a moment. There is no null, no nil, no none that secretly exists everywhere waiting to crash your program. Instead, Rust has a type called option, and a num defined in the standard library with exactly 2 variants, sum, which wraps a value of type t, and none, which represents the absence of a value. When a function might or might not return a value, its return type is option of something. The caller sees this in the type signature and must handle both cases before they can access the underlying value. The compiler forces you. No accidental null pointer exceptions, no silent. None propagating through your codebase, no getting a value where you expected one and crashing on the next line. The example on screen shows first word, which takes a string slice and returns option of string slice. If the string is empty, there is no first word. We return none. Otherwise, we return sum wrapping the word. The caller uses match to handle both possibilities. This is one of Rust's simplest and most life-changing ideas. Tony Hoare, who invented the null reference in the 1960s, later called it his billion-dollar mistake. Rust's answer is option. Enums and match are made for each other. Match, as we saw in Lesson 3, compares a value against a series of patterns. When the value is an enum, you list each variant as an arm, and Rust guarantees you handle every one. If you forget a variant, the code doesn't compile. And here's where it gets really valuable. As you evolve your program and add new variants to an existing enum, the compiler points you to every match expression in your entire codebase that needs updating. That feedback loop transforms how you refactor. The compiler becomes your pair programmer, tracking every case you might have missed. Consider the example. We're matching on a message value. We handle each variant, quit, move with its X and Y fields destructured, write which carries a string, change color with its 3 color components. The exhaustiveness is guaranteed. Add a new variant to message tomorrow, and this match breaks the build until you handle the new case. Compare this to switch statements in other languages, where forgetting a case results in silent bugs that only show up when the forgotten input actually arrives at runtime. That whole category of bug in Rust is impossible. Sometimes you only care about one variant of an enum, and writing a full match with an explicit underscore catch-all feels like overkill. Rust gives you if-let for this exact case. It runs the block only if the pattern matches, and you can pair it with else for the no-match case. In the example, we have an option of integer. If it's sum, we pull the value out and print it. If it's none, we print nothing. If-let is purely syntactic sugar for a match with one pattern and a catch-all, but it makes simple code noticeably nicer. You'll use match when you want to handle many variants distinctly, and if-let when you want to do one thing only when a particular variant is present. There's also a related construct called while-let, which repeats a loop as long as a pattern matches, great for draining a queue or reading from an iterator until it's empty. Both are small conveniences that make everyday code feel more natural. While we're on enums, let me show you the one you'll see most often in real Rust code. It's called result, and it's the foundation of Rust's entire error handling story. Like option, result is just an enum from the standard library, but with two variants, OK, wrapping a successful value of type T, and wrapping an error value of type E. It's how Rust models operations that might fail, without using exceptions. You'll see result everywhere, in file input and output, in parsing strings to numbers, in networking, in database calls, in anything that interacts with the outside world. The example on screen shows parseAge, a function that might succeed in parsing a string as a number or might fail if the string isn't a valid number. We return result of U32 comma string. Success is a number. Failure is an error message. The caller matches on the result, handles both cases, and life goes on. We'll cover error handling in full in Lesson 10, but know this. Everything you've learned about enums and match applies directly, because result is just an enum. Match patterns in Rust go far beyond the basics. You can destructure the data inside a variant, pulling out each field into a local variable. You can ignore the fields you don't care about with an underscore. You can match on a specific, literal value inside a field, not just binding the value, but requiring it to equal something specific. And you can add a guard, an extra condition prefixed with the if keyword, that must also be true for the arm to match. In the example, we match on a move message. The first arm triggers only if x is exactly 0, destructuring y into a local. The second arm destructures both x and y, then uses a guard to require they be equal, a diagonal move. The third arm catches all other move values. The final underscore handles every other variant. With all these pieces together, match becomes a declarative way to describe every possible shape your data can take and exactly what to do in each case. It's one of the features that makes writing Rust feel less like writing and more like modeling. That's enums and pattern matching. This is the part of Rust that tends to genuinely change people's minds about what a type system can do. Option eliminates null errors, match eliminates missing cases, exhaustiveness turns refactoring into a guided tour. Next up, Cargo, Rust's build and package manager. See you there.